Alright, we finished chapter 9. Now we are on chapter 10. Chapter 9 discussed carbonyl containing compound aldehydes and ketones. So a ketone had a carbonyl with 2 carbons. An aldehyde had at least 1 hydrogen on the carbonyl. It could be 1 or 2. Okay, so we discussed those ketones, and these two guys are general representation of aldehydes. But those are not the only carbonyl containing compounds. So we'll discuss carboxylic acids, okay, which will have this general structure. This could be a carbon or a hydrogen. The smallest carboxylic acid is called formic acid. Formic acid. Most of the bugs and the insects will inject this into you. That's why you'll feel an itching sensation when you're bitten by an insect. It's either this or ethanoic acid that is going to be in their venom. So that's the general structure of carboxylic acid, with this being the carboxyl group and their derivatives. So if you replace the OH with OC, you get an ester. If this is a carbon, so esters will be of that type. Or if you replace the OH with an NH, you get an amide. If it's NH, or let me just say NR2 group, the R here could be H or carbons. 2 carbons, 2 H's, 1 carbon, 1 H. Doesn't matter, you get an amide group. Okay, and there are other derivatives. For example, if you replace the OH with a halogen, the best halogen could be a Cl. We call that an acid chloride. Other people call it isochloride. So those are the derivatives, esters, amides, isochlorides, and we also have anhydrides. Okay, so you're looking at a carboxylic acid here. That's an oxygen, that's a hydrogen. So I think that ring looks like this. Okay, that's a carboxylic acid group right there, and also to the left you have it. But let's dive into the chapter so that we can discuss more about carboxylic acids now that we did ketones and aldehydes. Let's talk about carboxylic acids and their derivatives. So the main feature again is the carboxyl group, which is this group which can be written this way. You see you have 2 oxygens and a hydrogen, so this could be one way of writing it without showing the inner bonds. So that's the carboxyl group. Here you could have another group. You can represent it this way: our group and the carboxyl group, or these 2 oxygens can be written like that with 2 as the subscript. And the derivatives could be of this form, where again the X could be an OH. The X could be an OC for an ester, or the S could be an NR2 for an amide, or the X could be a halogen. Okay, S can be a halogen. So if it's a halogen, then you have an isochloride. Okay, so usually the OH is replaced by something else. That's how you get the derivatives to make the amides, to make the esters or SA halides or anhydrides. So those are the derivatives written down here, that point. So how do we name carboxylic acids? The priority is going to be given to the carboxyl group carbon. So we start from that carbon 1, 2, 3. You look for the longest chain. So identify your substituent. Here it's a bromine, but it's a substituent, so it's a bromo, and it's on the second carbon, so 2-bromo. There's no other substituent, so the substituent name is listed first. And then you notice that you have 3 carbons, so it would have been a propane. So for carboxylic acid, the E part is replaced by OIC, so propanoic. So prop for 3 carbons on the longest chain contain the carboxyl group, and then you include the propane, and then oic replacing the E in alkanes. But you still have to say acid because a carbox it's an acid. So it's 2-bromo propanoic acid, and that will be the UPAC name. There is a common name. You see the bromine is on the alpha carbon. Remember what we said about alpha hydrogens and alpha carbons in ketones and aldehydes. Whenever you have a carbon directly bonded to the carbonyl, it's called an alpha carbon. So one carbon over is going to be called beta carbon. So the bromine is on the alpha carbon, so the common name can also be alpha bromo propionic. This time you use pionic, not propanoic. It's propionic acid because you're using a common name. But don't think I'll ask on these black common names. I will just need the UPAC name. So again, prioritize the carbon of the carboxyl group because it bears the carbonyl, right? So that will be the structure. So this will be 1, 2, 3. The double bond, the CC double bond doesn't get priority. Priority is the carbon of the carbonyl of the carboxyl group. So you have 3 carbons again, it's prop, but there's a double bond, so one would have called it propene because there's a double bond. But you drop the E suffix alphabet and replace it with oic, so you get propenoic. It's an acid. So there's no substituent, so that will be the name, and that will be acrylic acid that we use to make polymers. That will be the common name, acrylic acid. Alright, next, again prioritize this carbon 1, 2, 3, 4. The OH becomes the substituent. It's on the third carbon or the beta carbon, third carbon or beta carbon. So when OH is a substituent, it's called hydroxy. So it's 3-hydroxybutanoic acid because there's 4 carbons on the longest chain, otherwise called 3-hydroxybutyric acid. See, the common names usually tend not to follow rules, so it's very hard to remember them. You might want to memorize them. That's why I'm not going to test you on those. I'll want the UPAC. Okay, so what happens if you have an aldehyde part on the structure and a carboxyl part? Here, the carboxyl will win. The carboxyl will win. If you had an aldehyde and a ketone, the aldehyde wins. If you have an aldehyde or a ketone and a carboxyl group, the carboxyl will always win. Okay, so you have an aldehyde here. So we will just have to represent that carbonyl. We're not going to call the aldehyde as a substituent. So we use a special word oxo, special infix word oxo in the name. So still the carbonyl of the carboxyl group gets priority. You have 3 carbons on the longest chain, so one would have called it propane, but the E is going to be replaced by oic, propanoic. The oxo is on the third carbon in the longest chain bearing the carboxylic acid, so it's 3-oxopropanoic acid. So this oxo part takes care of the aldehyde carbonyl. Okay, in this case you have a ketone. You see you have CC and a carbonyl, so in this case you have a ketone. At the same time you have the carboxylic acid, right? So we're still gonna use oxo but you have a substituent which happens to be bromo. So B and O, who gets priority in writing the name? It's the B. The bromine, it's on the second carbon, so 2-bromo. The oxo, which happens to be the carbonyl of the ketone, is on the fourth carbon, so 4-oxo. And then you have 5 carbons on the longest chain bearing the carboxyl group. It should have been pentane, but we're dropping the E, we are putting OIC. So it's pentanoic acid. And so on and so on and so on. So here this table is just listing the type of acids. Remember, this is formic acid or methanoic acid. Formic acid or methanoic acid. Guess why it's called methanoic acid? The reason is only one carbon in this formula. I told you this is found in ants mostly, and the Latin, of course, is formica or formica, because it comes from ants. Common name is formic acid. UPAC name is methanoic acid. 2 carbons in the acid is ethanoic acid, UPAC name. Others called acetic acid, which is the active ingredient in vinegar, and some insects or wasps. Then you have propionic acid, which comes majorly, you find it majorly in milk. Okay, propionic acid, common name propionic. Beta will contain butanoic acid. Valerian root will contain valeric acid, common name of pentanoic acid. And then, of course, some parts of the goats will give you hexanoic acid, or even in goat milk, and so forth and so forth and so forth and so forth. Okay. You do have acids that have double carboxyl groups. So like this one is called ethane-dioic acid. So you see how we have 2 carbons, so it's ethane. But you have 2 carboxyl groups, so it's di because there's 2 carboxyl group, and then oic because they're carboxyl group. They're carboxylic acid, so it's ethane-dioic acid. And then this one has 3 carbons. You can start from left or right. So you still have 2 carboxyl groups, so it's still dioic acid, but because of the 3 carbons, it's propane. Okay. Malonic acid found in apple. Oxalic acid found in some oxalic family plants. And then here, of course, you have 4 carbons. You see you have 1, 2 on the carboxylic acid and 2 more in the repeated CH2s. So for this structure, let me draw it down here. One would have written the CH2 twice. That's what this subscript means. So you have 4 carbons, 1, 2, 3, 4, numbering from left or right. So that's why it's butane and dioic acid, because there's 2 carboxyl groups, and so on and so on. Alright, so do you know that carboxylic acid will also, dicarboxylic acids will also have isomerism? So when you have a double in between, cut it across and then assign priorities following Kernighan rules. The hydrogen has atomic number 1, carbon here has atomic number 6, so this wins. Same as this side on the right, this will win. So the carboxyl group on the same side across the cut double bond in this maleic acid, so we call it cis. Alright, so if you are to number, it's 1, 2, 3, 4. So the alkene is on the second carbon of the longest chain bearing the carboxyl groups, so it's 2-butene, right? Remember, we always give the full name of the alkane or alkene. 2-butene, and then 2 acids, so it's dioic acid. Okay, that would have been how to write it, but it's actually the UPAC name is I think this is the UPAC name, this is the common name. So here if you cut across, the carboxyl groups are opposite, so we give it trans 2-butene-dioic acid. There are aromatic acids also. So like this one is called phthalic acid. This one is azophthalic acid. You see how now the carboxyl group is one carbon over, there's a carbon between them, and this is terephthalic. These guys, especially this one is used to make polymers. If time permits, we'll do the chapter on polymers. This is used to make painkillers or drugs in industries like ibuprofen and so on. This one can be used to make other important organic molecules in the lab. So let's practice and write these structures. So A, 3-hydroxyhexanoic acid. So where would I start? I'll start with the parent name, hexanoic acid, meaning I have 6 carbons, including the carbon of the carboxyl group. 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Those are my 6 carbons. Starting from here, this will be carbon 6. Okay? And then the hydroxy implies OH on the 3rd carbon. So 1, 2, 3. The OH will be on the 3rd carbon. And that takes care of A. Okay. B, octanoic acid. I mean, this carboxyl group could also be on your left, but I just adapted writing it on the right for some reason. So it's octanoic acid, including this carbon. I should have 8 carbons on the longest chain. 2, 3, 4, 5, 6, 7, 8. So this should be carbon 8. Okay, I have 2 iodo. So the iodine is on the 2nd carbon. So it should be here. That's my iodine or iodine, whichever way you call it. The methyl is on the 2nd carbon. So that's my methyl. And that takes care of it. 2 iodo, 2 methyl octanoic acid. Next, C, 2-butionic acid. So but means 4 carbons. It's a carboxylic acid, but you see how you have a Y, so it means it's an alkyne. So the alkyne, the first carbon is on the 2nd carbon of the longest chain. The first carbon of the alkyne is on the 2nd carbon of the longest chain. That's what this 2-butyne means. And then I need 4 carbons. So that will be it. Remember, it should be linear. So I would have just drawn it like this, and that should take care of it. Okay, where this is 1, there's a carbon here, 2, 3, 4. And then D, 5-ethyl 6-oxoheptanoic acid. So looks like we have a carbonyl somewhere in the longest chain. But anyway, we have 7 carbons. So I'm gonna put my first carbon there, 2, 3, 4, 5, 6, 7. And then hept means 7, that's why I put 7 carbons. So this is carbon 1, 2, 3, 4, 5, 6. The carbonyl is on the 6th carbon. That's what the oxo means. It happens to be a ketone. Oxo is used for ketones and aldehyde carbonyls whenever they show up in presence of the carboxyl group. Okay, so we are moving from carbon 1 to carbon 7, and then you have an ethyl on carbon 5. So that is my ethyl there, and that should take care of it. Away from nomenclature, let's look at the derivatives. Now, remember our carboxylic acid was like this. So if you chop off the OH, replace it with a Cl, you get an SO, otherwise called acid chloride. You get an SO group or acid chloride, which is this. If you replace the OH with this ester looking structure, you get anhydride. Okay, if you replace the OH, okay, with an OR group like OCH3, you get an ester. If you replace the OH with an amine, you get an amide. Okay, so you can convert this to that by SN2 with your nucleophile of choice. The nucleophile could be this. So you can imagine just using this, attacking the carbonyl, and this falls off. You get that. You can convert this acyl chloride by SN2 using OR negative as a nucleophile, which will just knock out the Cl following similar arrows like I did. You can convert the acyl chloride to the amide using NH2 minus or ammonia. The anhydride can similarly be converted to the ester or amide. The ester can convert it to the amide, but notice that the amide cannot be converted back to the other groups because NH2 is not a good leaving group. This Cl minus a good leaving group, O negative or R, those are good leaving groups. So you can switch them with the groups by attacking. You can switch them with these groups by attacking the anhydride or the Cl with these nucleophiles because these are good leaving groups. This is a good leaving group because it's resonance stabilized after it leaves. Cl is a good leaving group because it's electronegative. So it holds on the electron, stabilizing the leaving group. Okay, but these guys usually have a hard time interconverting because they're less reactive. That's what this slide is trying to imply. Okay, so if you were to rank reactivity, the acyl chloride will be more reactive than the anhydride. Okay, and the anhydride will be more reactive than the ester. Okay, the ester is more reactive than the carboxylic acid. The carboxylic acid is more reactive than the amide. So the amide is the least reactive of all of them. Okay, that will be the ranking of reactivity. And I'm saying reactive meaning can we lose these leaving groups? Reactivity goes with whether you're gonna lose those leaving groups. Okay, so carboxylic acid are acidic, of course. Their pKa is approximately 4.5 to 5, so they're acidic. The lower the pKa, the higher the acidity. Okay, but they're not acidic as HCl because HCl tends to have pKa between 0 and 1. They are more stronger acids that you can get even with negative pKa's. So as with alcohols, they form hydrogen bonds. So it's possible that when you have two carboxyl groups, you'll have hydrogen bonds. So let's discuss the physical properties of carboxylic acids. Their pKa is lower than 7. We say that the lower the pKa, of course lower than 7, the higher the acidity. So they are acidic, but they are not acidic like as HCl, which will have negative pKa. Okay, no, negative is less than 0, so HCl, for example, is very acidic compared to your carboxylic acid, but at least it has a lower pKa of 5, which means it can lose that hydrogen too. Even weak bases like sodium bicarbonate, let alone the strong bases like sodium hydroxide. Alright, so the other physical property is they form hydrogen bonding just like alcohols. Remember what we said with alcohols? Hydrogen bonds can be made when OH is bonded to oxygen. When hydrogen is bonded to oxygen, or hydrogen is bonded to nitrogen, or hydrogen is bonded to fluorine. Those are the bonds you look for in a molecule to decide whether you make hydrogen bonding between the two molecules using intermolecular forces. So what you're looking at here is hydrogen bonding. And they are IMFs because you have two molecules, so it's intermolecular. they exist between two molecules, forces, IMF. So in alcohols, we said that oxygen is more electronegative. Alcohols and water, of course, because H2O is similar, has similar structure to alcohols. So oxygen will be partially negative, hydrogen partially positive. So you can imagine having an oxygen close by here. So in between the two molecules, you're gonna get the hydrogen bonding. So do the same thing for carboxyl acids. You do have lone pairs. This hydrogen is partially positive, the oxygen is partially negative because of dipole moments. Because of dipole moments, this is partially positive, partially negative. So you expect the lone pair of one oxygen of another molecule to bind or to get attracted to the hydrogen of the second molecule. You get two hydrogen bonding as shown here, but you can get more because you still have lone pairs here, which would help hydrogen bonding to occur. You can get several hydrogen bonds, and that's what makes carboxylic acid to have high boiling point, and some of the organic carboxylic acids are solids. Okay, so if you can compare the boiling point, because the carboxylic acid has so many chances of doing hydrogen bonding as shown here, you're gonna have high boiling point. Okay, because there's so many chances of hydrogen bonding with other molecules. Okay, there's so many chances. This oxygen can do it here, can do it here, can do it there. OH only has one chance, so to speak, there. Or we can say two if you want, because it can also hydrogen bond to another molecule here. Okay, so you see, the more the chances of making hydrogen bonds with these lone pairs, the higher the boiling point, because whenever you're boiling, it's these hydrogen bonds that you're cutting. You're cutting there, you're cutting there, you're cutting there. Whenever you're boiling, you're trying to cut the intermolecular hydrogen bonds. So if there are many, then you're gonna need high temperature to break those bonds, because bond breaking requires input of energy. It's endothermic. Bond breaking is endothermic. So that's why carboxyl groups, carboxylic acids, will have higher boiling points than alcohols. Okay, and alcohols will have higher boiling point than esters. You see here, there's no hydrogen bonded directly to oxygen, so there's no hydrogen bonding. All you have is gonna be dipole-dipole, so the boiling point is lower. Now, because of the hydrogen bonding, small carboxylic acids are highly soluble in polar protic solvents like water. Now, why are carboxylic acids more acidic than alcohols? So this is an alcohol. The pK of alcohols is roughly 16. pK of carboxylic acid, we say it's roughly 5. So why are carboxylic acids more acidic than alcohols? Pretend that you're gonna lose the hydrogen. Okay, use water as a base. To take out that hydrogen, these two electrons go to oxygen. You're gonna end up with an alkoxide. Now, if you draw the structure of the alkoxide, you realize that there's no way you can do resonance because there's no double bond next door. But if you do the same thing for carboxylic acid, so let me draw the Lewis structure. So I can push the mechanism taking out the acidic hydrogen, donating the 2 electrons to this oxygen. The result would have been what we call a carboxylate. Remember, I talked about carboxylate in the last lecture. Carboxylate, we use ATE because this is a salt. It's negatively charged organic molecule. You get your carboxylate, and of course you're gonna get your hydronium, because after water abstracts the hydrogen, you get an extra hydrogen on the structure of water, which gives you H2O+. Anyway, this becomes a conjugate base. The conjugate base is resonance stabilized because I can push an arrow here and that one there, you get your resonance structure, where now the negative charge goes to the oxygen above. This was neutral, now it's negatively charged, and you make a double bond on the oxygen to the right. So the reason why carboxylic acids are stronger acids than alcohols is because your conjugate base is resonance stabilized. Okay, the more stable the conjugate base, the weaker it is. Okay, so this conjugate base is weak base because the electrons are not available, they are dancing back and forth by resonance, right? The weaker it is, and the stronger the parent acid. So like I said, the more stabilized the conjugate base, the weaker it is. Here it's stabilized by resonance. If it's weak, then it must have come from a stronger acid. Here the alcohol gives you an alkoxide. That's a strong base. You know that's a strong base. We used alkoxides for E2 to take out beta hydrogens to make pi bonds. If it's a strong base, then it must have come from a weak acid. It must have come from the weakest acid of the two parent molecules. Okay, so like I said, once you make your carboxylate, the carboxylate is resonance stabilized. That's why the carboxylic acid is a stronger acid than alcohol. Okay, because the alcohol will give you an alkoxide, the carboxylic acid will give you a carboxylate, which of course is resonance stabilized. You push your arrows like this, that goes there, you get this resonance structure. And of course, if you want, you would have pushed this pi bond towards the oxygen, which is unlikely. Lewis structures try to minimize charges. We talked about that in chapter 1. These are the two common resonance contributing structures. So I think you get the idea here. Okay, so where are you getting your this coloration here just simply means that you are having a high density of negative charge. Okay, so here the negative charge is over here and over here, and we try to minimize that. That's why these two guys will give you this cartoon of electron spread, and it shows that it's a little bit less colored than this, so the electron distribution here is better than here. So these are the two acceptable resonance contributing structures. Okay, now what happens if you want to rank the acidity of carboxylic acids? So you look at their structures, because most likely I'm not going to give you the pKa's. What you need to do is to look at the structure and spot the difference. So pKa can be affected by what's on the structure of the carboxyl group, and that effect is caused by inductive processes, electron pull or electron donation through bond, okay, which happens from the alpha carbon, which is the carbon next door. So now, if I were to draw the Lewis structure to see the comparisons, here I have 3 CH3s. So you see here you have here I have 3 hydrogens, here I have 2 hydrogens on the alpha carbon and an R group. You all know that the R group is an electron donating group through bond. Okay, and then here instead of the R group you have a halogen. You know that halogens are electron withdrawing group, so that's an electron withdrawing group. Electronegativity increases across the periodic table. So chlorine is more electronegative than carbon and hydrogen if I'm to compare these groups. So you have electron donation, you have electron pull. Which one do you think will give you a stronger acid? Now, without looking at the pKa, let's look at the bases the conjugate bases that will be formed once this hydrogen is lost to a base. So let's say you have a base that will take out this hydrogen, like we did in the previous slide. You're gonna get this carboxylate. Remember again, we are comparing the hydrogen to the carbon to the chlorine. If the same thing happens here, this is the structure you get. with O minus after this is gone. If the same thing happens here, where the base pulls out this hydrogen and donate the 2 electrons between O and H to this oxygen, you're gonna get this structure. So remember what we said? We said the weaker the conjugate base formed, the stronger the parent acid. So if the pKa of this molecule is the lowest, that means this is the strongest acid. This is the strongest acid of the three, and the reason is because the chlorine is even helping to suck electrons towards it, making these electrons not available, which makes this the weakest base of the three. I'm comparing structure A, B, and C. This will be the weakest base. Why? Because the chlorine is pulling electrons towards itself from this oxygen. So the weaker the conjugate base, the stronger the parent acid. So this parent acid has a pK of 2.86. If you are to compare this and this, the CH3 is donating electrons more than the hydrogen. So this structure B will have more electron density around the oxygen, so it's going to be the weaker acid of the three because the metal is donating. If you want to get a strong acid, you have to be pulling away. The hydrogen has less donating effect, so the pKa of this ethanoic acid is 4.72. So always look for what you have. Electron donating groups will make the carboxyl group a weaker acid. Electron withdrawing groups like Cl will always make the carboxylic acid a stronger acid out of the set. Not the strongest acid possible in the universe, but out of the set given to compare. Okay? Alright, so the chlorine pulls electrons. Now, what if you have this situation? In this case, we're going to consider distance alongside inductive effect. So what is the effect of distance of the substituents alongside inductive effect on acidity? So I would like again to spot the difference. All you have here are hydrogens, right? You have 3 hydrogens, you have 2 hydrogens, you have 2 hydrogens, no chlorine. So there's no electron drawing group that will make this molecule a stronger acid. So this is the weakest. Okay, so ranking from 1 being the strongest to 4 being the weakest, this will take number 4 because there's no electron drawing group that will stabilize the conjugate base. The conjugate base would have looked like this. No electron withdrawing group to stabilize the conjugate base. Here you have it. Here you have a chlorine that will pull electrons. Okay, so if I were to draw the conjugate base, like I said, the best way to approach it is to look at the conjugate base. Okay, so the Cl is pulling the electron density from this oxygen that has a lot of it. But the problem is this Cl is on the 4th carbon, so it's further away. It's just like long distance relationship. You really have to struggle to make it work. But at least you have a Cl compared to this molecule A. Okay, so this second molecule is a stronger acid than the first one because at least you have an electron drawing group, even though it's farther from the O minus. So do the same thing here. Our conjugate base after losing the acidic acid will look like, after losing the acidic hydrogen will look like this. This time the chlorine is on the 3rd carbon, so it's closer to the O minus, so it has a higher effect on electron pull through bond, which is inductive effect. So like I said, we are considering both distance and inductive effect. Look at how far it is. So this is a stronger acid than this. Molecule C is a stronger acid than molecule B because the Cl is closer to the farthest oxygen. Now this Cl is on the 2nd carbon, so obviously if I draw the if I draw the conjugate base, you can see that there is stronger effect because it's very close to the oxygen. You see how I only pulled 4 arrows here, 3 arrows. Here I pulled 1, 2, 3, 4 arrows. Here I pulled 1, 2, 3, 4, 5 arrows. So the closer the electron withdrawing group, the greater the electron withdrawing. Okay, the effective cumulative. Let's see. So let's see. Before I talk about that, so this helps stabilize the conjugate base by shifting the charge density away from the farthest oxygen atom, but distance must also be considered. Okay, so the next one is how many electron withdrawing groups you have. This one does not have electron withdrawing groups, right? The ethanoic acid here does not have electron withdrawing group, but 2-chloroethanoic acid has it, but it only has one. This one has two. So you see the change. The lower the pKa, the more acidic. So this molecule is more acidic than this. Molecule C is more acidic than molecule B because it has two electron withdrawing group. Okay, so if you were to draw the conjugate base, then you get O minus, which will lose the electron density more because you have two things pulling the electron density through bond and they're closer to it. So here there are two electron withdrawing groups, here there are three electron withdrawing groups. You'll expect that there's going to be a higher or stronger stabilization effect on the conjugate base once the acidic hydrogen is lost, because you have three things pulling. It's just like playing the tug of war and you have three stronger guys. You're gonna win by pulling the group on this side. So in this case, you are pulling the electron density towards the chlorine, spreading the electrons on the structure. So molecule D is the strongest acid of all because it has three electron withdrawing groups. How do we form salts from carboxylic acids? Now, because you know once the carboxylic acid loses the acidic hydrogen because it's bonded to an electron withdrawing group, you're gonna get a carboxylate. And like we've said, the carboxylate is resonance stabilized. So because this is acidic, you can use a base. Allow me to redraw the structure so you clearly see the effect of the base. Remember what I said. Metals will be spectator ions because they're just cations. So the main ingredient here that plays the role of a base is the hydroxide group in sodium hydroxide. So use this to take out the hydrogen because we know bases are proton acceptors. So the OH minus is accepting this proton, and then this bond with the two electrons goes to the oxygen. The oxygen had two lone pairs. Now the oxygen will have three lone pairs. Do the formal charge calculations, it will be negative. We call that a carboxylate, so it's a salt. That's how you form salts from carboxylic acid. You use a base. Like I said, you can also use sodium bicarbonate to do the same because these carboxylic acids are acidic. Now, because these are salts, they are soluble in water. Why? Because obviously you see that here there's an ionic property. Okay, so the conjugate base is soluble in water. Now, the OH that takes out the hydrogen makes H2O because now you have two hydrogens on the structure. This used to be OH, now it accepted the hydrogen, now it's water. So you make what's called a carboxylate. So carboxylic acid can play a role in acid-base neutralization reactions. Okay, because they're acidic. Okay, how do we prepare acids? The first preparation we'll talk about is from oxidation. So remember we said primary alcohols can be oxidized to aldehydes. but if it's strong oxidizing agent, does not stop at the aldehyde, goes to carboxylic acid. That's one way. We also say that aldehydes can be oxidized to carboxylic acid using silver oxide, because aldehydes are reactive. Oxidation is addition of oxygen. You've added an oxygen here. Here you've added an oxygen there. You can also use Tollens reagent to oxidize the aldehyde to carboxylic acid. Now, one can also oxidize side chains of aromatic compounds. So I'm gonna introduce you to a word. Okay, so this carbon here is called benzylic carbon. So if the benzylic carbon has at least, if it has at least one benzylic hydrogen, then you can oxidize and chop off the structure and create a carboxylic acid. So like here, that's a benzylic carbon, right? It's sitting right on the benzene, so it's benzylic carbon. Does it have at least one hydrogen? The answer is yes. In fact, it has two. So what you need to do is to chop off the rest of the carbon structure and just put the carboxylic acid on the benzylic carbon. So that's what has happened. That's the benzylic carbon is still there, but it has been transformed to the carboxylic acid using potassium permanganate at heat. The other reagent that can be used to oxidize the benzylic carbon to carboxylic acids is oxygen presence of cobalt-3 and acetic acid. Okay, so industrially they would use this reagent or potassium permanganate to oxidize the benzylic carbon. So remember, I said you need to note that you need a hydrogen atom on the benzylic carbon. The length does not matter. You make benzoic acid. Without a hydrogen atom on the side chain, the side chain is oxidized to a carboxylic acid but requires harsh conditions. So if there's no, you see like here, there's no benzylic carbon. There's no benzylic hydrogen. So in which case you don't expect the ring to have the benzylic carbon oxidized like that. This won't happen. Instead, it's the side chain that's gonna steal the carbon and make the carboxylic acid. So instead, you're gonna get this structure where this carbon came from the ring and the ring will scramble. Otherwise, this is what I would want you to know. This is just for your information. What I want you to know is that if I give you this and I give you Jones reagent, okay, not potassium permanganate, if I give you Jones reagent, because potassium permanganate I told you is very harsh, this reaction is very messy. So let me say that I give you potassium, let me say that I give you chromic acid, okay, conditions, Jones oxidation. If you have Jones oxidation with this, because there is no benzylic carbon, there is no benzylic hydrogen, then the answer will be no reaction. Okay, so in other words, let me show you what I mean here. So let's say if you have a ring and let's say it looks like this, and then I tell you you're using Jones oxidation, right, to oxidize, the answer here will be no reaction. Why? I look at my benzylic carbon, which is the carbon sitting on the ring, and I see there's no benzylic hydrogens. There's no hydrogen there. You already have 4 bonds, so you cannot oxidize the benzylic carbon, so there's no reaction. But if I had this, if I had this structure, now I have a benzylic hydrogen. So if I do the same reaction, it's possible to oxidize my benzylic carbon to a carboxylic acid. So the rest of the chain, regardless of how long it is, will just gonna be transformed to a carboxylic acid. That's your benzylic carbon right there. It's converted to a carboxylic acid. Now what if I had this ring? Okay, I do the same reaction. Okay, benzylic carbon oxidation. I have at least benzylic hydrogens there. I have at least one benzylic hydrogen here. So I'm simply cutting across and inserting my carboxylic groups on the benzylic carbon. That's your benzylic carbon, is bonded directly to the ring. This is your benzylic carbon, is bonded directly to the ring. Those two will bear carboxyl group. Okay. But again, if I do this, okay, now my benzylic carbons don't have benzylic hydrogens. They don't have it. So with the same reaction conditions, no reaction. Unless I use potassium permanganate, which will be messy. We'll continue from there.